Well, let me remind you where we finished, because these are Newton's, all versions of Newton's second law are really important, because they, really it is that from them we figure out how interaction is related with motion, and all the other theorems like work energy theorem, impulse momentum theorem, they all are derived from Newton's second law. For an object, rate of change, we found out yesterday that the rate of change in total momentum of an object is equal to the net external force exerted on the object. Internal forces don't really matter how total momentum of the object is affected. You could recognize actually that this version is similar to a version for a particle, right? Because for a particle we have that a particle cannot exert the force on itself, so there are no internal forces, only external forces exist for a particle. So we have exactly the same thing, that net external force exerted on a particle, and then total momentum of a particle overlaps with momentum of a particle. So over here we see why is it that I know that in the past, although the first two versions of Newton's second law of motion we discussed was always for particles, but very often you put objects, and I didn't really penalize you, I just much for putting object. Now we have a basis to put objects rather than particles. And well, on the next slide actually I'll show you why center of mass becomes when I suggested that if we approximate object by a particle, why we should think that that object is at the location of the center of mass. Why center of mass identifies location of the object. So I'm going now to relate momentum of a particle with the motion of center of mass. So, and why don't you help me? Where did I get this from? I wrote this letter represents now total momentum of the system of particle, or of the object. And I wrote that this is sum of products of mass and velocity of individual particles constituting the object. Where did I get this from? This is the definition of total momentum. Total momentum of a system is equal to the sum of momenta. Now, because look at me when I walk, and think about me now as a system of particles, and look how particles of my body move. Can you see that there are parts of the body that although I am walking, yeah, because when you think about my walk or my motion, you pick a point almost intuitively already, somewhere in the vicinity of my center of mass, where it would be. Over here? Somewhere over here, right? So you look that my position is associated with the position of this particular point. And when I walk, I was trying actually to move in such a way that my center of mass moves with a constant velocity. But do all parts of my body move with constant velocity? Yeah, look at the foot, which is in contact with with the floor. I'm walking, but the foot is not. The foot stands still. Now, if you look at my palms, actually, my hands, they even sometimes move backwards. I mean, I will exaggerate it now. And you can see that that hands are moving backward in the opposite direction than I am. Well, my total momentum, when I calculate my total momentum, I will have now to consider various parts of my body differently. So for example, head, which is moving almost parallel to my center of mass, will have the same velocity as the center of mass. Particles of my foot, which is in contact with the floor, these particles will have velocity 0. And one hand will actually move twice as fast as I do, and the other hand is going even to move in the opposite direction. I would have now to add these momenta to get total momentum of my body, by definition. All right, where did I get this from? Instead of velocity of ith particle, I wrote that it is rate of change in the position of the ith particle. It comes from the definition of velocity, correct. Well, this step is a mathematical step, right? I wrote that the sum of derivatives is equal to derivative of sum, and here I put a constant inside of the derivative. Well, I took this derivative outside because I recognize that this is a sum which appears in the definition of center of mass. If I divided this sum by total mass of the body, I will get position of the center of mass, which means that this sum over here is just equal to mass of the object multiplied by position of the center of mass of this object. Well, I will make now another mathematical step to take out mass in front, and I got, what did I get over here? Mass of the object times rate of change of position of the center of mass. Do you see that? Which means that, what does it mean now? Well, instead of having rate of change in momentum of, rate of change in position of the center of mass, by definition it is velocity of the center of mass. What did I get now? That the total momentum of the object is equal to total mass of the object multiplied by the velocity of the center of mass. So now when I walk, although my foot doesn't move and hands move backward, my total momentum is indeed equal to my mass multiplied by the velocity of just one point associated with my body, the center of mass. So in a conclusion, total momentum of a system of particles is related to the velocity of the center of mass of the system. I have here a simulation of, well, let's think now about Moon and Earth as single object. I remember when I spoke to my colleagues, who is an astronomer. Actually, we are relatively small planets, so in principle we could even consider that the system Moon and Earth is a double planet system. Okay, now let's see how actually motions of various objects, and think about objects, these objects, I mean the Moon, the Earth, and the Sun, how it looks from various points of view. I'll start from the reference frame of the Earth, which is good for all engineering purposes. But if we look at the motion of stellar objects, see how it is going to, how the motion of objects are going to look like. Center of mass of the Moon and Earth will be somewhere in between over here. It's moving in a circular motion. Earth is obviously stationary. Moon is circling the Earth, and the Sun is wobbling. It's getting closer and further away from us. Now, can we recognize, can we discuss inertiality of this reference frame? Is Newton's second law satisfied in this reference frame? You have, you say shaking means no, or shaking means no idea. Well, anybody has an idea. Well, let's think about how the object should accelerate. Does the acceleration of the Moon make sense? Yes, there is a strong gravitational force. We can ignore the gravitational force exerted by the sun. There is a strong gravitational force exerted by the Earth, which results in centripetal acceleration. So it looks fine. Motion of the moon looks fine. Now, how about motion of the Earth? Does this one make sense? Does motion of Earth satisfy Newton's second law? Well, let's draw a free body diagram for the Earth. What forces are exerted on the Earth? Is the net force 0? Why? Because what? No, don't. Well, making conclusion that because acceleration is 0, then the net force is 0 is not right, because how do we know that Newton's second law is valid in that reference frame? First, we have to recognize, we have to make sure that the reference frame is inertial reference frame. Then, force and acceleration are proportional. In general, remember, net force is not proportional to acceleration. Shout it to your neighbor. Correct. It is proportional only to certain acceleration. What acceleration? In an inertial reference frame. Correct. Right? Now, so, and recall that when we link motion with interaction, we have to analyze both independently. Yeah, we look at the configuration of the universe and we figure out how the object interacts. We can indeed have problems in which we try to determine force exerted on something from acceleration when we want to design a system. We want a certain object to move in a particular way, like a spacecraft. We want a spacecraft to travel really fast to escape from the gravitational field of solar system, for example. Then we will have to design what forces we would need. But in order now to execute that, we are not changing acceleration. It is that we just have to make sure that the configuration of the universe will be right. So it is that the Voyager has to pass, for example, big planets in order to get accelerated. Do you understand me? All right. So over here, I also want you to do the same way. Look at because indeed, if we wanted Earth to be still in a particular location, and if we look at that location from an inertial reference frame, we would have to make sure that we put that Earth in the location where the net force exerted on it is going to be 0. But the net force exerted on it is going to be determined by the objects around, not that we manipulate acceleration. All right, so take a look at the objects around. What objects do we have around? The moon, right? And the sun. All right. Is the force exerted on Earth 0? No. Because moon is attracting Earth, and this is the major force. Well, sun is actually attracting both of them. So, in the reference frame of the Earth, motion of the Earth doesn't satisfy Newton's second law. The net force exerted on the Earth is not 0, however, the object does not accelerate, which means then actually for this problem, the reference frame of the Earth is not inertial. Newton's second law is not satisfied in that reference frame. Well, in the engineering problems, we are not looking, we are actually, the accelerations which we are interested are much greater than these. We are interested in what will happen in few seconds. Yeah, it doesn't have to collapse in few seconds, or it has to accelerate in few seconds. We are trying to make cars so that they accelerate from 0 to 55 miles per hour in what? I don't know. Less than 10 seconds. Yeah, if it accelerates in less than 10 seconds, then the driver is really excited about it. Yeah, I have a nice car. All right, let's now take a look at another reference frame, the reference frame of the center of mass of the Earth and the Moon. Oops. So now this is how the objects are going to move. Does this make sense now? Well, if we look at the Earth and then the Moon, they both experience centripetal acceleration. They both move in a circle. Problem is the problem now is with the Sun, though, because the Sun is also going to move with the circle. So for these two objects now, the reference frame of the center of mass of Earth and Moon is a good reference frame. Now, even better reference frame is if we choose the Sun as the reference frame of the Sun. Well, in the reference frame of the Sun, then both Earth and Moon orbit their center of mass, and as this entire object circles around the Sun. Sun is still much heavier than these two objects around, so its acceleration is approximately 0. So if we, obviously in the reference frame of the Sun, acceleration of the Sun is 0, so we still see that that reference frame is also approximately inertial. All right. I mean non-inertial. Let's now take a look at the expression for gravitational potential energy of an object, not of a single particle, but of an object. So let's say that I have this object over here, and let's say that at this location the object has potential energy 0. Now if we move it up, what will be, so this location is the reference location for the potential energy. Now if it moves up, what happens to the potential energy? Well, I would refer now to the total potential energy, total gravitational potential energy. So by definition of word total, I have to add potential energies of all particles constituting the object. Now, if it is near the surface of the Earth, gravitational potential energy of a particle depends on the height of the particle. So change in potential energy from this location, now those particles don't have actually to be in the same configuration. The object doesn't have to be moved in parallel. Actually, it can even change a shape. Yeah, so for example, I can consider that this is my reference for potential energy, and I can calculate my potential energy as I get up. My shape completely changed. However, for each particle, the change in potential energy, this should be initial, for initial height. So it will be mg final height of particle k minus mg times initial height of particle k. Over here I have already right. So I can take in front acceleration due to gravity, and I will be left with this and rearrange the terms. Now I can recognize that this sum is equal to mass of the object multiplied by the height of the center of mass, final height of the center of mass over there. And this sum is total mass multiplied by the height of the initial location of center of mass. So gravitational potential energy is going to equal to total mass of the object times acceleration due to gravity times height of the center of mass above the reference location. So it's height from the center of mass when the object is here to the center of mass when the object is there. So for example, now let's think about it that let's say that this is my reference for potential energy, because I cannot get lower. So my center of mass is approximately at this height now. See that? Well, when I change my shape, center of mass move over there. Let's say that my mass is about 100 kilograms. Estimate by how much my gravitational potential energy increased when I got up and changed the shape. Talk to each other. Estimate it. For simplicity, assume that my height is about 2 meters. It isn't, but it's easier to calculate. So by how much did I raise center of mass when I got up? How much? Maybe a meter. It's not exactly, it's less than a meter, but let's say that I raised the center of mass by a meter. So by how much did my potential energy increase? For simplicity, also assume that the acceleration due to gravity is 10 meters per second square. How many joules? 1,000 joules, correct. My mass is 100 kilograms, acceleration due to gravity is 10, and I raised the location of the center of mass by 1 meter, so 100 times 10 times 1 gives me 1,000 joules. I increased my potential energy, gravitational potential energy by 1,000 joules. So again, you can see that for the engineering purposes for which we make small objects, gravitational potential energy or work done by gravity when we consider an object as a particle is really associated with the position of the center of mass. It's not in general though. If you are getting, if your body will get close to black hole, for example, which over there the gravitational field is very non-uniform, so I wouldn't be able to pull out that G from here in front. Then that formula won't work. However, we have very few engineering problems in the vicinity of black holes so far. I wouldn't even advise you to approach one, because your body would be ripped off immediately. You will be accelerated, and the acceleration will be acceleration of let's say that you are flying with your legs forward. The force exerted on the legs would be much greater than on your head. Well, so just gravitational acceleration of the legs, if the objects were loose, if the parts were loose, would be much faster. You could maintain your shape only if you applied very strong internal forces in the neck, for example. The neck would have to be very strong so that the head would follow the legs. All right. Let's skip that. Now, I want to bring up another version of Newton's second law, which this time I want actually to relate acceleration of the object, acceleration of the center of mass. So I'm going to start with the previous version of Newton's second law to find out. Oh no, maybe I don't. Let's try to find out mass, product of mass and acceleration of the center of mass of the object. Help me, where did I get this from? I wrote that acceleration of center of mass is equal to the second derivative of position. It's not exactly from definition, but from two definitions, from definition of acceleration and from definition of velocity. Right? Velocity is derivative of position, and acceleration is derivative of velocity. Therefore, acceleration is second derivative of position. All right. Now, instead of this vector center of mass, I wrote this expression. Where did I get this from? From the definition of center of mass, correct. I have to multiply each particle, mass of each particle by its position, add those products, and divide the result by the total mass of the system. Well, now this is a mathematical step. Derivative of this expression, derivative of a sum is equal to sum of derivatives, and m actually cancels over here. See that? Now what is this? Acceleration of the ith particle of that object. So I can write down that this is mass times acceleration of the ith particle. Now acceleration of the ith particle is determined by the net force exerted on the particle. So I can write down that is the net force on the ith particle. I mean this acceleration of product of mass and acceleration. Now I separated again forces which are exerted by other particles of the system and the external forces. Why did I separate those which are internal forces? Because remember, I can use again the same trick that the sum of all internal forces on all particles of the object is going to be how much? 0. Because Newton's third law says that if ith particle exerts certain force on jth particle exerts opposite force on the ith particle. Which means that this sum is going to be 0, and I will just get the net external force. So mass of the object multiplied by acceleration of the center of mass of the object. In a slang, we associate acceleration of the center of mass with acceleration of the object. But for a while, I don't want you to use phrase acceleration of the object anymore. For 2 weeks. For 2 weeks, I don't want to hear phrase acceleration of the object. What do I want to hear? Acceleration of the center of mass of the object. Yes?
So is the acceleration of the center of mass of the object technically like the acceleration of a particle in you, or
No.
what?
No. It's, the question is the acceleration, so is the acceleration of the object acceleration of a selected particle in my object? A center of what particle?
Center of mass particle.
A center of mass is not a particle. Yeah? But then you are correct about that. Yeah, because acceleration of the object is indeed associated with the acceleration of the center of mass. This is what we really mean when we say acceleration of the object. But I don't have a ring. Well, but if anybody has a ring. Oh. All right. It's a tiny ring. Where is the center of mass of the ring? In the hole in the middle. Now I will toss it. It was moving in a crazy way. Yeah, even like that. Yeah. So the particles really they were accelerating in a funny way, very funny way, because they interacted with each other. So they were pulling each other. So actually, if I flip it like that, centripetal acceleration due to that rotation is much greater than acceleration due to gravity. However, if you look at this ring as the object and you say that it was, because really, center of mass of this object was accelerated only due to gravity, gravitational force exerted on this object. So, but we don't have a particle at the center of mass. Thank you. Do you understand that? So, indeed, now actually you have the justification. Why did I ask you to associate object with the center of mass when we are approximating objects by particles? What did you say?
The center of mass may not even be in the object.
Correct. Yeah, like over here, center of mass is not in the object. Yeah, but this Newton's second law says that the net external force exerted on the object is equal to total mass of the object multiplied by acceleration of the center of mass of this object. All right. Now, I also want to introduce not to introduce, but modify appropriately or consistently work energy theorems. If you now recall how we derived work energy theorem from Newton's second law, you would recognize that I'm doing now exactly the same thing, except that rather than observing location of a particle, I'm just following the location of the center of mass. So I will now calculate a product of external force and displacement of center of mass. Well, from Newton's second law, I can write down that external force is equal to mass of the object times acceleration of that object. This quotient over here is acceleration of the object. Can you see that? It's a rate of change in, here I have change in velocity of center of mass divided by time. But here I had another differential. So actually it doesn't matter which differential in the numerator I will divide by dt. So now I will conceptually switch it and think about this expression. So rate of change of the position of center of mass. This quotient gives me rate of change in position. Right? So I can write down that this is velocity. So I will have mass times velocity times differential of velocity. Velocity of the center of mass. Well, I wrote it that way because now I can recognize that v dv is a differential of a certain function. If I have x dx, it's a differential of what function? X squared over 2. X squared over 2. Because, differential of a function, I have to take derivative of that function and then put the variable, right? So I can recognize now that this expression over here is a differential of such a function. Now, it's easier to see it that way. Yeah, I know that somehow we learn, because we learn it first that way, then we don't see it this way. Yeah, so take a look what I'm going to get if I differentiate this expression and express it in terms of variable v. So I can take m over 2 in front and then take derivative of v squared. Derivative of v squared is 2v. So 2 and 2 will cancel, so I will get indeed mv, and then I write the differential of the variable. Now, if I look at this, because it is total mass of the system times velocity squared divided by 2. The unit of it is what? What are the units of the product of mass of an object, square of speed of the center of mass divided by 2? What will be the unit of this expression? Joules, correct. Joules. Because kinetic energy is also measured in joules. This expression is similar to the definition of kinetic energy. What's the difference between this expression and the definition of kinetic energy? Because tell me the definition of kinetic energy. Can anybody tell me the definition of kinetic energy? 1/2 multiplied by what? Mass of the particle, not the object, of the particle. So far we had definition of kinetic energy for a particle only. So it is mass of the particle times square of speed of the particle divided by 2, right? Now over here we have something different. We have mass of the object times speed of the center of mass of the object. I'm glad that, because I would be really upset. I told you not to use the speed or velocity of the object for 2 weeks. It is speed of the center of mass of the object divided by 2. Which now also resembles, gives a justification why, when we approximated object to be a particle, I ask you to consider that the particle is at the center of mass of that object. However, since this is an object, not a particle, an object can change shapes, can change rotation, we don't call it kinetic energy. This is not kinetic energy of the object. Can you read what it is? Translational kinetic energy of the object. And don't forget to use this adjective. Yes, Taylor?
Why do you have the centimeter subscript?
It is not centimeter, it stands for center of mass. I'm sorry. This subscript refers to center of mass. So, for example, let's say that each of those balls has a mass of 1 kilogram, so it will be easier. What is kinetic energy? And let's say that it drops. One ball drops for a second. So if it drops for a second, what will be the speed of that ball? 10 meters per second, correct. Tell me what is the translational kinetic energy of those 2 balls? Translational kinetic energy of those 2 balls. And so is mass of this one is 1 kilogram, of this one is 1 kilogram. This one doesn't move, this one moves with the speed of 10 meters per second. So what would be the translational kinetic energy of the 2 balls? Tell me, what should I add? What should I multiply? Definitely we will have 1/2. 2 kilograms. And now square of speed. What should I put there? Speed of center of mass, correct. Now where is center of mass if these 2 balls are identical? Right between them, right? So if one ball doesn't move, the other ball moves 10 meters per second, how fast the center of mass moves? 5 meters per second. So over here we would need to put 5 meters per second. Let's now figure out kinetic energy of a ball. Single ball. What should I put? 1/2 times 1 kilogram times 10 meters per second square. Which one is greater? Second one is greater. Look, that kinetic energy of a single particle was greater than the translational kinetic energy of entire object. How about total kinetic energy of this object? How big was total kinetic energy of this object? How much? Well, should I use this one or another one? No, that one is translational kinetic energy, not total. Ah, yes.
Kinetic energy of ball 1 plus
Correct. We have to add kinetic energies. Kinetic energy of this ball plus kinetic energy of that ball gives me total kinetic energy of the object. Now, make sure not to confuse those three kinetic energies. Oh, actually, no, even more. Four kinetic energies. Yeah, for those two balls, I can think about four kinetic energies already. Tell me what do I have in mind? Kinetic energy of ball 1, kinetic energy of ball 2, total kinetic energy, translational kinetic energy. Correct. Now here we're talking about translational kinetic energy, and we found out that the change in translational kinetic energy is equal to net force exerted on the object multiplied by the displacement of the center of mass of the object. It looks like an expression for work. Can you see that? And we call it work. However, we call it work done on the center of mass. So if I come back again to the two balls and I drop one, how do I determine the gravitational work performed on that system? Let's calculate gravitational work exerted on that system. Oh, actually, even better than that. Work done by me. How much work I do, which affected translational kinetic energy of that object. Did I perform work? Great. I'm happy about this because I heard both answers, yes and no. Only one is right. Yeah, because each of you, I mean, what you are doing, you are confusing works. So those of you who said one, you did it wrong. I'm not telling you who is wrong. So who thinks that I do perform work which affects translational kinetic energy? That I did perform that work? Raise your hand. Who thinks that I did perform work? Who thinks that I didn't perform work? Why did you think that I didn't perform work? Oh, let's start with this. Did I perform force? Did I exert force on the system? Yes, where? I was supporting that ball. Yes, I was pushing the system up over here. It doesn't matter that I didn't keep this one. But I was pushing up. All right. So the force was not zero. Anybody changed now his or her mind that I did perform work? Who changed the mind that I did perform work? Why did you change your mind? Because I'm holding this one up, and where is the displacement? Where do you see the displacement? Which one? So I have to multiply this force by the displacement of this ball to find that work? Yes, Jessica, what do you think? Actually, you are right. He said that I should consider displacement of the center of mass to calculate that work. And center of mass did move. Right? So I did perform work on the center of mass of the system. Now, those of you who said that I didn't perform work, why did you say that I didn't perform work? Because there was no displacement of the particle on which I did exert the force. So, work on the particle on which I applied force was zero. but work on the system was not 0. Okay, we'll come back to this tomorrow, and please review the 4 versions of Newton's second law and the 3 versions of work energy theorem. Tomorrow I'm going to bring up a 4th version of work energy theorem, and we will play to make sure that we do not confuse those concepts.
I have a question. When you're talking about the acceleration of the particles inside the object, doesn't it change the acceleration of the internal? I don't know. What I'm trying to say is a gyroscope which has something going on inside affects